let me, have we start?
Yeah, this recording is going on. Yeah.
Okay. Hi, hello everyone. Welcome to another session of Book Club. So for the last two sessions, we have covered the chapter 1 of designing data intensive applications and the first part of the chapter 2. So today we will quickly go over the chapter 1, whatever we discussed in our last session, and then jump to the second part of this chapter. So the second part is not huge one. I think we covered most of the chapter 2. So we hopefully will be able to cover it within our 45 minutes that we have. So so the way I think, like most of you already know the format. So it's just like we'll go over the summary of the whatever we read in the book, and then discuss on the questions, and if anybody has real world examples or anything like that. So that's the format. It's pretty open. It's nothing like uh, somebody's teaching anything. So feel free to jump in, ask questions, or share your thoughts on it. So what we discussed last week was like the first part of mostly discuss the differences and advantages and disadvantages between the initial models, which is like relational model and the data model. We discussed about some concept like impedance mismatch, where there is a mismatch between what is needed in the application versus how the data is stored in the database, and how are the data, the different kinds of data, which is like some of the data which needs like one to many relationship, some needs like many to one and many to many relationships kinds of data models that we need to handle. And we talked about it also discussed the book actually discussed about how uh, relational data model works well with different kinds of relationships, like specifically for many to one and many to many relationships, versus where document model was good with handling one to many relationships. And also we talked about the book talked about uh, s- uh, the schema flexibility that is with document model uh, versus a relational model, and also like how schema is maintained, specifically topics like document model has a schema. I mean, like it's not completely schema-less as we talk. It is like it has a schema needed on read. The schema is maintained on read, versus like relational was like when you write it, you have to make sure you follow the schema. And it also talked about data locality, where how uh, the data locality has helped for the document models versus relational models, where the data is split across into different tables and stuff. So that's the brief summary. And the second part, so I'll also quickly go over the second part summary. So any questions or anything people want to discuss for the chapter 2? This part? There is some background. Abhijit, do you mind? Yeah, thank you. Okay. 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 So coming to the second part of this chapter, the author discussed about the query languages for the data. So he discussed about two types of query languages that we have. One is a declarative kind, and the other is an imperative kind of model. So imperative is more of like how we write in the programming model, like where you actually use loops and you write all the conditions that are needed, and you kind of control everything to query the data. Whereas in declarative, the system, the language provides us ways to actually query the data and filter it. Like if you look at SQL is one good example of the declarative data. And he talked here about IMS and Codacil query languages, which are more of imperative. I haven't used them, so I'm not too familiar. but based on the example they have given there, it looks more like how you write your own, uh, how you parse the data by using for loops and all of it without really using the database optimizations or anything like that. So, and he talked about like how having that kind of a language uh, helps, like having the optimizations implemented in the database engine, which helps for multiple queries. And I think he also talked about um, how parallelization all is taken care in case of declarative languages versus imperative languages. He gave examples of the same, how the declarative queries are used in the CSS and XSLTs using XPaths, where a similar declarative kind of approach is used. So those are a couple of examples. SQL, CSS, and DOM APIs are a couple of examples of the declarative kind of examples. So people who have used them might be familiar, like how that is being used. So I've used mostly SQL, and I see that how that helps. And then he introduced MapReduce. I think we have a specific chapter 10, where there's more about this MapReduce and how it is used. Here he specifically talked about MongoDB, how MapReduce is used. He gave a couple of examples. He talks about how it is a combination of declarative and imperative kind of it. It specifically, I think this MapReduce concept is also available in a lot of functional programming. Is like it is generally used while processing large bulks of data and the distributed kind of data. So that's an example, and I think it's pretty famous. I believe, like I don't have like first-hand experience of using MapReduce, but most of my experience is reading the concepts about MapReduce, how you group the data, filter the data, and represent the data, which is like the map reduce and represent it. So uh, I don't know if anybody have a first-hand experience of using MapReduce, or like, is there any better way of explaining MapReduce? Does anybody wants to share? I know it's quite famous, and I think it's being used in multiple places now. So anything anyone would like to share on that?
Hey Naga, Dippy here.
Yeah.
So, I mean, I haven't used MapReduce from industry, at work,
Mhm.
but I've used it like in small, back in school exercises. So, I mean, maybe I can just kind of talk a little bit about there, but if anyone has deeper experience, feel free to chime in.
Sure.
So my idea of MapReduce is like you explained, right? It's just like a two-phase programming model. Map is basically used on the subsets of data. So you take the full data set and
Mhm.
then try to break it out and pass certain subsets of data to this map function, and each of them works locally on that set of data, so they're not like interdependent. And
Mhm.
then reduced phase is where all of those analysis that is coming from those subsets is actually merged to give a global final answer. And I think one of the examples that is out on, as a kind of a hello world for MapReduce is like the word count example. So if you pass it certain lines of text to this, a function which is written using MapReduce style, then what it will do is, let's say it takes first 5 lines and it passes it to, uh, a map function. Then it takes next 5 lines and that also gets passed to the map function. And each of them actually do this, word count, like key value pair. For example, if we can take this line, right? MapReduce is a programming model. So in this case, if I pass this line, this sentence, then my map function, let's say it's written in a way that MapReduce will map to 1, like it's 1 count right now. If I see the word MapReduce again in that subset of data, then it will be MapReduce 2, right? The word like frequency count sort of thing.
Mhm.
And Similarly, so that is just one subset of data. Let's say another subset that we pass to map function that also has certain MapReduce words, right? And there, let's say the frequency comes out to be 3. So if you think at the high level, we have two subsets with their own local counts. And now when you pass it to reduce function, then it kind of, pulls those two different frequency counts and, it can sum them up, 5, and that's your final answer for this. But I mean, the high level idea, as I understand, is it's about breaking your computation, right? With map function doing, and in this chapter, I think you will also maybe talk later about it. But I remember like this point where one of the use cases of following this model is that this map function and reduce function, they are written in such a way that they're kind of, they can operate on that, data within them independently. They are kind of self-contained. So it
Yeah,
helps
yeah,
to break your computation and then, yeah.
yeah. He talked about that that way of.
Right. So I
Actually,
have some experience regarding this. So basically, a real life example would be something like this. Let's say you have uh, a time series database wherein like people say you're getting data from a sensor, but let's say you are getting stock market data, okay? And maybe the data is pretty large. So let's say it might be 80 GBs, 90 GBs. So now the first thing that you want to do, maybe you want to calculate rolling averages, rolling averages over 2-minute bucket intervals, let's say. So every 2 minutes you want to see what is the average price or something like that, let's say. So then like what are the strategies? There might be like one way, right? You keep it just in one box and you keep going one by one. So every 2 minutes you slide it and you again calculate it. So that might be one way of doing things. The other way of doing it might be you split the data into multiple chunks and then apply the rolling averages to each individual chunk, and finally you report together. So what I have seen in my experiences, generally what happens is people generally, so a lot of things they placed, a lot of people what they do is they place the big data into HDFS. HDFS would kind of split the, so there would be this name node. This name node would be splitting them into the data nodes, and each data node will have a certain portion of the data. So let's say a 10 GB a 10 GB file would be split into 10 nodes and each containing 1 GB. Now what you do is you write a map kind of job, or you write it, or either the vendor who's using MapReduce, that person would be giving a job that would run against each node, and finally all that nodes can go to a single reducer, or there can be multiple reducers in the middle, because you can do multiple level of aggregations. And then what happens is you get the final result. So generally I have seen that MapReduce gets used in kind of batch processing, wherein basically you have a huge chunk of data and you don't really care about how much the, it's like, I wouldn't say care, I would say the latency, it is not so latency sensitive, wherein basically you don't need to keep stuff in memory. So generally how I have seen things happen is a map job will run, it will write to disk, there is a reduce job which will read from the disk, it will do its calculation, and maybe again it will give to another reducer to do final reducing stuff like that. So two things, yes, it breaks, so it works on the subsets of data, which has been broken down into smaller chunks, A. And second thing is it is generally used for batch, because when the map and in the map and the reduce phase, the map phase will be writing the intermediate data to the disk, and that will be read by the reducer. Yeah, that's what I have seen. Yeah, that's about it.
yeah, cool. Thanks, Deb. I think that's a good explanation, both DP and Deb. So, is it like it's mostly used? I mean, like it makes sense to use this in a lot of distributed systems a lot, right?
Yes,
Because
it does get used in large scale queries I've seen. So So generally what happens is when the data size is large, only then do you benefit from these things, because what happens is if you work on a very small data set, then setting up the map jobs, so everything takes time. So setting up a map job takes time, setting up a reduced job takes time. So if you just use it on a 1 GB of data and you split it across like 4 boxes, it is not going to yield much benefit. But if the data size is huge, then what happens is that you are basically processing the data across multiple nodes, and then what happens is the initial startup cost that is there to set up this entire infrastructure of map jobs and reduce jobs, they kind of get nullified by the advantage that we get in parallel processing. So that's what I've seen.
Makes sense.
I have in your case, is that the data a live feed into the sub session, or like it batch and it all the data going once and it process?
So basically how it is happens is, so it's not live data, first of all. So this data, so the data that I'm talking about is the stock market data, and like it has already happened yesterday, let's say. And what we are trying to do is we are trying to do some kind of bulk analysis based on the entire day's data. Maybe there is a generally what I've seen is, like, if we combine the transaction data, which is like the order data, if we combine the market data, and if we again market facing data, so that would be combined would be like 300 gigabytes at least, like 300 gigabytes or 400 gigabytes as the minimum that you would have. So, and it is not something which is updating regularly. It's a data which we have received yesterday, and we are working on top of it by dividing it into batches. I don't know if that answers your question.
Yeah, it does.
And the one other thing I see, like on Deb's point, is when we use this model, like I think it's also about when the data is large enough and you split your data across nodes. Now, rather than moving your data to a compute node, right, you can have the map function, which is a small chunk. You can have it on every node. So you're rather than moving your data, you're moving your sort of compute, so as to say. So that can be another.
Yes, I agree with you, because what happens is, like, moving data over the network can be very
Yeah,
expensive.
yeah,
So if someone has experience with Apache Spark, so they would know that like if you join two big RDDs, there can be several problems, right? Because
mhm,
moving data across the nodes. So
yeah,
so what we are trying to do is we are trying to move the compute to the data, not the data to compute.
correct, yeah.
Not
So all of that can be done in parallel, right?
Yes, it can be done in parallel. That is true.
But the last one, the reduce, is that have to be like,
Yes, it
it
depends on
cannot
the
be done.
dependence. It depends on the dependency graph, right? So like so if you think about it, if you are doing an average of, let's say so you're doing an average of 1 GB of data, let's say I'm taking the marks of this is a hypothetical situation, so I'm taking the marks of the students of the of all of India, and then what I'm doing is I'm like I have, let's say, 100 GBs of data. Then what I want to see is, okay, what is the average? Then what happens is individually I can keep the averages here and in each chunks, and then once all the averages is done, you can do it in the reducer. So that would significantly reduce the time that is required to do the average rather than just doing it at one place, right? So that's the advantage. Obviously reducer, if there's a dependency, there are multiple reducers, the whichever stage we are, the the ones that are further down in the pipeline would depend on the finishing time of the previous ones. That's always there.
Yeah, but eventually, Dave, I think to Leon's question, I think his question is ultimately at some point there has to be one reducer, right?
Yes, there has to be. There will be more.
Yeah,
So basically, there would be a one sync at the end.
yeah, yeah. Right.
Yeah, that's true.
cool. Yeah,
So,
that was
yeah,
good.
I mean, what people have said is correct, but I mean, like, uh, moving the data is actually cost between the nodes is costly. That is why the whole MapReduce thing started. But that was the initial phase of where, I mean, it only works for the companies like Google or Facebook. So if you actually see, if you actually use Hive or some, I mean, MapReduce, generally they don't maintain the HDFS architecture. So the way, so generally people now store the data in S3 or something, I mean, some other similar Azure or some other cloud storage. But whenever you run queries in Hive or some other Spark or something, the data nodes and the execution nodes are actually different. So the Hadoop, I mean, the
No,
MapReduce
so
itself is,
in my
yeah.
understanding, like I don't know about S3 because I haven't worked with Hive and S3, but at least in the Hadoop world, I can say is like there are two versions, right? So if you think about the latest Hive, they call it, there is one concept, there is one engine called the LLAP. So basically what they do is here they try to keep everything, so they run daemons. So let's say there's an Hive or Impala, let's say let's talk about Hive. So Hive will have let's say 10 nodes it is installed on. So some slaves are there, some master is there. So you will fire the query on one and it will be processing. So if you look at LLEP, they would be storing most of the stuff. If it is latency is an issue and if you want to query it in real time, they will be storing everything in memory, most of the part. And there would be a mix of keeping it in memory and some part serialized to disk. So and that would be like the serialization part would be on a high speed SSD. So that kind of setup is done. So I don't think it is always in memory. So it depends on what mode you want to write, what mode you want to query. It can be a batch or it can be a in memory thing as well, depending on what you
No,
choose.
no, no. I was not talking about the execution. So I was
Mhm.
saying that the where the execution happens and where the data resides, they are actually
Mhm.
quite different now. I mean, MapReduce actually started so that only code can move, the logic can move, but
Mhm.
the data doesn't have to move. That it
Mhm.
started with that ideology, but now it is totally different.
Mhm.
You don't actually maintain your HDFS architecture and the MapReduce architecture, the where the execution happens.
So
So
what architecture is maintained there?
the, I mean, the way the execution happens and where the data is, I mean, unless you are maintaining your HDFS architecture and the execution node architecture, the the execution doesn't happen on the same node. If you are using cloud or something, the execution differs from the
Oh,
data
yeah.
node.
So you're talking about decoupling of compute and storage sort of thing.
Yeah, the compute and the storage are completely different when it goes back when it goes to the cloud.
Mm-hmm.
Okay.
I
So
mean, since
how is
most
the
of the
do you know how is it achieved? Because like I am a little I'm not clear on this, because let's say I place I have my compute at some other place. Let's say logically, if I
yeah.
think about it, if I kind of compute at Ohio, I have my something, or maybe in West Virginia I have my data center place. So how would the compute happen? It
So
will
it
move
depends
data
on,
over the network, right?
yeah,
Yeah,
it will move the data or the network.
yeah, it will move the data. I mean, I don't have experience either, but I'm thinking aloud. And Uday, if you have experience, you can chime in more about it. But I'm thinking that even if we are moving data in this model, the benefit here would be that you're kind of moving subsets of data, and you can do that in parallel rather than hogging the bandwidth like of one big data set, right?
But you are hogging the bandwidth of the network, right? If you think about it.
No, no, it's not like compared to the first model. Yes,
Mhm.
you are like, taking network resources. So it's not
Mhm.
saying that it's kind of some way overcoming that limitation. But I think it's more, as I'm understanding, it's kind of trading it off, right? If you follow this compute and storage decoupled model, then you are probably
Okay.
getting some advantage there, but you are sacrificing this network.
I'm not sure about this because, like,
Yeah.
let's say, if things are placed across two data centers, then data, you would be moving a lot of data from one data center to another. So,
Correct.
is
Yes.
that advisable? Because
I
you'll
know,
be
I know in real world systems, it is happening, but I never looked at it from the perspective of, like this MapReduce and data model.
okay. Okay, so I do not have enough insight into the how the things are working with cloud, and so I cannot comment on that. But yeah, that is my experience with Hadoop and how things are done there. So Uday, if you have any real-time experience, then probably you can share.
I worked on a problem that mitigates this actually. That's why I kind of know. So the thing is, I mean, what people have said previously, saying that it executes parallelly on different machines, right? So that is correct. That is the reason why they still use MapReduce. But when you go to the cloud, the data and the execution differs completely. So, I mean, even in the MapReduce, there's a concept of split, right? So every split is distributed to different set of machines in the cluster. I mean, when you maintain a Hive cluster or Spark cluster, so each split is kind of a data in itself, and that job is assigned to that one of the node, and that they read parallelly. I mean, so you say that these many files, the first 20 files read by this one machine, the second 10 set of files read by this another machine, like that.
So if that is the case, is the machine that is reading the file and the machine where you basically the reading job is run and the place where you place the files, is it the same? What do you think?
No. You
They're
read it
different.
from, they're different.
Okay. Okay. So probably I'll do some reading and then it might become clear for me. Right now, I do not have any insight into it.
Yeah, okay. So why worked on a similar problem, that's why I was able to say. So basically we have I worked on an optimization where you can read from the local nodes than read from the distant storage. I mean, in the cluster, most of the nodes will be co-located. So instead of reading from a cloud storage, if the data has been already read, you can actually read from the nodes that
Okay.
have already read.
That makes sense now, because you are saying that it is co-located, right? So if things are co-located, then definitely that issue of transferring the data might become slightly lesser. I don't know if it was
Also,
something
there
like
is there's some concept around network attached storage. These are just like kind of, I mean, just high level ideas, but I don't have deep information.
No. It's not actually network storage as such. So
Okay.
basically, when you issue a query, query on a table, some select query or something, some part of the data might have been already read by some previous machines. I mean,
Yeah.
other machines in the cluster. So you have issued another query, which might have to run on the same data itself.
Okay.
So you
Caching
can
stuff.
actually read from the other nodes which have already read instead of reading from the cluster. I mean, the cloud storage.
all right.
Interesting.
Yeah.
Just as a time check, should we kind of maybe walk? Yeah.
Sure. That was an interesting discussion. So
Yeah.
I think actually chapter 10 is completely about batch processing and MapReduce. Probably I think that's where he discusses more about those things. So here I think he's only comparing like how MapReduce is both declarative and imperative language here. So I think that's what he wanted to introduce here in this chapter. Just give me one moment, guys. Sorry, guys. My son just woke up and he's like, he's coming to talk to me. Okay. Okay. I think with that, we can move to the graph models. I think with graph models, he wanted to introduce like how many-to-many relationships are very well handled with the graph model kind of databases. In this, he introduced two types of graph models. One is property graph model and triple store model. So I think property graph model is kind of which is which is a bit famous. I think like I have heard about those things in many places. Like I think Neo4j is one of the graph models which is a bit famous. So in property graph models, the way it is like the graphs that we talk about, where you have a node and you have vertices, and node has some properties and vertices has some properties, and each node has like the incoming and outgoing, which is like the relationships, the incoming relationships and outgoing relationships defined on it. And he talked about the query languages that are available. Basically, from what I have seen, based on my experience, what I have seen, we don't have a real-time project, but based on what I have seen, the same kind of data, whatever we are representing in the graphs, can also be represented in the relational tables with maintaining the foreign keys and all this stuff. But when you query for the data in the graph models, what I have seen is like the joins are already defined and calculated for you. So the cost of creating the joins on the fly on every query in a relational database is more costlier than when the joins are already defined in the graph model and the queries are easier and faster. And even if you look at the languages like Cypher, you can see like the very limited code because the queries are optimized with all the joins available. Whereas if you write a similar query in the relational database, we saw that like there is like huge query you have to build and you have to define all the joins, and that joins are a bit costly. So
Yeah,
that
I have real-time experience working on this as well. So in Neo4j, so we had this problem structure, problem statement wherein what we wanted to do is like when we received this order data, right? When a user splits, so what we basically do is, let's say a client places an order and he wants to get the best execution on the stock market, right?
Mhm.
So there are several intermediate components which basically splits that order into smaller orders, okay?
Mhm.
And they get routed to different exchanges via different paths. So that's how it is. So now this data is maintained in a transaction list. So you can think of it, it's mentioned in maintained in a DB somewhere. Now let's say if you had to query, so if you want to calculate that, okay, I have placed an order at time T1, okay, and I wish to see when it hit the market, okay, and let's say if there is a delay while going through the different components, I want to calculate. That is one of the use cases. So you might want to trace the path from the time the order was placed to the time when the order hit the market, and you might want to trace everything, like as the order passed through the components, was there a delay? So is the problem statement clear? Probably then I can go and talk about the rest of the thing.
No, but this is not dynamic path, right? It's like a fixed path always.
No, it's not a fixed path, because let's say there are so there are, like, let's say 10 components in the middle, okay? So I might go via, so if you think of a route, then you might go via 1, 2, 3, and 8, or you might go via 1, 2, 3, 4, 8, and so on and so forth. So every time the order might traverse through different paths.
Oh, okay. Okay.
Okay. So, so did we take the right path? So the question here that we want to answer is, it's like not the minimum, cost. It's more like, did we take the right path? Did we take the correct decisions based on what was the scenario of the market at that point in time? So this was the use case, and we solved it using Neo4j. So what we did was, as the order was passing through, so it can be done in real time as well, by the way, with the enterprise edition. And so as the order was passing through the different components, we used to add it to the graph. Okay, so add it to the node, and as the order appeared, basically, and because it's like a tree kind of structure, so it had a parent. So you used to link it with its parent, and we used to now imagine if you wanted to do the same thing, you wanted to trace the path using SQL. How would you do it? That is a question. Anybody can like pick it up and think about it. How
So,
would you do it if you want to trace the path? Yeah.
so I think we would maintain different tables. We would maintain a relationship table where you have like, we say like, oh, this point to this point, we have a relationship or not as one table, and all the, and also a relationship type in that relationship table, where you have entries being made. Okay, there's a path from this to this, and a type is this one. I don't know if you guys are handling type, right? You don't need to have a type
We
of
don't need to have a file. We don't need to have a type.
Okay, then that case, like one table which maintains the relationship, saying that this point to this point, I have a path exists, and another table with all the points there. So if the path exists there, then you know,
So,
like, the path exists.
right. I see your point, but how will you maintain the path, right? So there has to be a way to maintain the path. So let's say I tell you that, the lowest mesh, I want to get the last order. I'm giving you the last order. How will you go to the root? So how will you go to the origin? So what kind of query? So probably we'll have to do multi-level joins, right?
Multi-level
Yeah.
joins,
So
dim table. Yeah. Yeah.
correct. So you can very well imagine that if the data size is huge, if it's like 20 GBs of data kept, and then you are doing multi-level joins, it will never come out of that query. So
Mm.
in such cases, GraphDB is very useful because we are building the relationships as and when the data is appearing. Okay,
Mm.
and then what happens is, like, when we are done with all the orders, at any point in time we have the latest view as to how the things are connected to one another. And
Mhm.
because the links and joins are inbuilt, we can very easily trace back, or go from the root to the child, or we can go back, we can start at any node and basically do any kind of traversal. Any graph algorithm that we can possibly think of, it can be applied in both directions. We can go down, you can go up, you can see the siblings, anything like that. So I think that's the strength
Yeah.
of graph databases compared to SQL.
Yeah, that.
Yeah.
Yeah.
Interesting.
And I had a similar use case in my PhD. So I worked on these graph databases. So, and just as a very quick thing, looking at the time. So what we did was, we have these multi-layered architectures. If you look into data warehouses, you have these operational data stores, and your data is coming in. There are some workflows happening, and then you're condensing your data, and then there is whole another process which puts it into a warehouse, and then you have all sorts of queries happening at different levels. So the question was, if you make a change to anything in that architecture, there is a very likely few other things will break if you are not careful enough. So what we did with graph databases was, how to model these relationships. And when the user wants to make a change, then rather than just making a change and breaking things and getting, all sorts of your application breaking, you can actually run that, a framework to get an analysis of the impact of that change. So similar to what they were saying, that with graphs, you can model relationships pretty, easily, and you can traverse them easily. So,
Interesting. Interesting. So yeah, that's good. So the problem that we didn't implement it completely, but the problem we wanted to use it for was like, in retail, like we have different kinds of products, right? So for example, you have a Nike shoes, and that has like, is a style of a uh, product, and you have different colors under it, and you have different sizes under it, and that product is sold in different departments in the company. And sometimes the product moves between the departments, and that is supplied by an original supplier, and but there are different vendors who supplies it, and that keeps changing and moving. So, and in those cases, like when these things are changing constantly, and when you want to query this kind of data, we tried to use this graph model where it was easy to query because we have defined relationships, and the movement was all easy. So that was one problem we wanted. We tried solving using GraphDB. So the good thing about it was like it supported heterogeneous kinds of nodes, that which author also talked about here. Is like once you define a node, it always need not be like a place or a person or anything like that. You can have this relationship between different kinds of nodes, and you can add new things as needed. So in our
Yeah,
case, it was like a new
that's
vendor
interesting.
came in. Yeah.
Yeah, I found it really interesting as well, because if tomorrow's the schema gets updated and like you want to add one more property and
Yeah.
you want to start querying, then it makes your life really easy as compared to
Yeah.
a equal kind of setup wherein you have this primary key, foreign key. Again, you'll have to readjust everything. You have to replace everything with nulls.
Like
So
schema
all that.
evolution is a challenge, right? In relation.
Yes,
So
correct.
that is very like handled well with graphs. And just adding to the heterogeneous point. So with the work that I did, that aspect was one of the key features. That if you look at the whole architecture, you have different kinds of artifacts. You have ETL workflows, you have schemas, you have queries, and the model is different, right? So graphs really help you to kind of come up with a canonical representation in terms of nodes and edges. So that was also good.
Good to know. We had a real world need actually of that heterogeneous types. So there are new kinds of vendors that came in who were supplying those products. So we had to create different kinds of nodes. So yeah. So did you guys find any like strong limitations on the graph TV, graph kinds of things? Because here the author did not talk about it. I believe there is like more that comes in. But I'm just curious, like, since you guys have used it, was there any strong limitations you had to face by moving to graph?
I think to me it seemed like, at least Neo4j, this is specific to Neo4j, I think it took a lot of resources as compared to, in terms of processing and stuff like that. It used to take a lot of resources as compared to, but again, it's like, it is very contextual, like how it is implemented and what you're doing, if you create an index and stuff like that. But I thought like what with the same amount of memory and stuff like that, I could do more processing in SQL. But again, the use case was very different, so I do not see a way to compare the graph database and SQL as such. But for the use cases, like both are meant for different use cases, right? One fits the bill in a different way, the other thing is a little different. So
Yeah. I think that's the summary of this chapter. Like each use case has its own needs and different data models needed. So use what is good. Yeah. Okay. So with that, I think we have like 1 minute. So there's one more model that he talked about, which is different from the property graph model, which is what we are talking about, node and like incoming and outgoing things. In the triple store model, he talked about where we have three things. One is like the subject, predicate, object. The way it is stored is like only with these three. For example, the example he gave is like, we are trying to represent this complete thing into the model. But with the triple store model, you can only store like a subject, predicate, and an object. Here it is like, okay, the person Lucy is married to Ellen. So that's all it could store. That's and like everything has to be stored in that model. That's what is the triple store model. Whereas in the graph model, you could have stored all of it in the complete as like one graph of it. So he had a couple of examples on like how semantic web has evolved. So I'm hearing the semantic web for the first time here, but I think this is where they wanted to use machine learning on all the websites from the website data. So and he talked about Sparkle and Cypher, which are similar kinds of languages. When I looked at the syntax and the examples he gave, I found that they're similar kinds of languages. Both are declarative to do the querying. I think Sparkle is more for triple store, and Cypher is more for.
Cypher is more like for Neo4j. It's actually
Yeah,
specific to Neo4j. Yeah.
yeah. Neo4j is one implementation of graph. Yeah.
Right.
Yeah.
And I think, Naga, I'll let you finish, but I just wanted to add something on semantic web, but maybe.
Oh, is it? Yeah. That's interesting. I wanted to read about it
Yeah.
more
Yeah,
because.
actually, I did an internship in semantic web. And it's quite interesting concept and quite ambitious. Very high level idea is that what they want to do is right now on web, there is all this information around. So like you said, using machine learning, right? So if you were to use machine learning, you have to label your data, which is on the web in a certain way. So what their aim is that all the data on the web is annotated, right, in this form like subject, object, predicate. And the idea comes from the fact that if I'm referring to a word, let's say, I don't know, I mean, like word orange, right? It can be a fruit, it can be a color. But if you have attached these predicates, then you can also have this entity matching going on. So if at two places I'm using the word orange and both of them are using the predicate color, then I know they are, you know, I mean, you can build relationships basically across heterogeneous data sets, and you can use like machine learning and whatnot. I mean, we can read it more, but I think that was quite an ambitious, yeah, interesting. There is a whole, research organization back in Ireland who actually do a lot of projects on semantic web.
Yeah. That was the interesting thing, right? It started like this machine learning on web was started. I think it was started way in 1980s or
Yeah.
1990s. That was interesting. I never realized that machine learning on web was started at that time. So that's the interesting thing. Today. Okay, I think data log. He talked about data log. I think it's pretty. It's not being used a lot nowadays. I don't think there's much in the current world systems where that is being used. So yeah, I think at the end, what he tries to conclude is like every problem has a different need of the data model, and so use as per the need is what he tried to conclude with the data model on here.
Yeah.
So I think with that, the chapter 2 is done. So probably we'll pick the first part of chapter 3 in the next session. So DP, I think we can stop recording. I just wanted to get consensus from that people